So today we will talk about the last method for solving divide and conquer problems, or solving the problems basically that can be approached by divide and conquer method. Okay, so the divide and conquer as a general method usually results in the solution in the form of recurrence equations. So we in the previous lectures we have talked about the two methods, right? The substitution method and the recursion tree. So this one, substitution method, is a more strict one that uses mathematical induction to prove some solution is true, is correct. But in terms of how to obtain some guess about the solution, using the recursion tree method is a very good option. It's like gives you an intuitive understanding of why we have some sort of guess for the recurrences. Okay, so the method, master method or master theorem that we're going to talk about today is provides a general solution to recurrences. Okay, and we will first introduce the method and talk about the usage, and we will also spend some time to look at how we prove that. Okay, but it is not required to fully understand how the proof is done. Proof is done, but the most important part is know all the technical details about when to use such a method. So yeah, I think the question in the chats is basically correct. The recursion tree method is a good way to come up with a solution, to have some guess about the solution. But from a mathematical perspective, if you want to prove that that a solution is a valid one, then you definitely need to use substitution method, to use the definitions of big theta, big O, which requires you to find the constant C, the boundary condition n0, and so on, in order to prove that solution. Okay, but it's not always necessary to use substitution method, but it's basically based on your need, right? If your need is just to have some rough idea about the running time of an algorithm, then given the recurrences, if you don't need a very accurate proof, then you just to use the recursion tree plots is a good way as some estimate to get some estimates. Okay, let's look at the master method today. Okay, so first of all, let's observe our previous conclusions. So we, in the last time, we have worked on these recurrences. It's 3 times t of n equals 3 times t of n over 4 plus c times n squared. Okay, I hope you still remember the meanings of these numbers. Okay, so in the case of divide and conquer, this quantity 3 means that after each, so when we divide the problem into subproblems, we will have 3 of such subproblems. And each subproblem is n over 4, is a quarter of the original length. Okay, so given this recurrence, our solution shows that it's basically this formation. It's some constant times c times n squared plus theta, the big theta of n to the power of this quantity. And we know that this quantity is less than 1. right? It's the logarithm of base 4 with base 4 of 3, right? So this big theta term is a lower order term compared to the quadratic term here. And so that's why we can write it as big O of n squared. Okay, so I highlighted these two parts, right? They are basically the same order. Okay, so this may give us some heuristic that it looks like the cost here, C times n squared, dominates the total cost. Okay, because the C times n squared, this quantity is the one you put in the root node when you draw a tree. Yeah, of course, in this case, there are 3 branches in each node. So when you do the first root node, when you draw the first node, you will put C times n squared there, right? So looks like in this case, the root node is the dominant quantity or dominance. It has the dominant order for the whole solution, because the whole solution is also a quadratic function. Okay. So it's just our guess. Okay. So one thing we can easily imagine is that, what if we changed a little bit for this recurrence? For example, if we don't have a C times n squared in here, if we have a linear term like n, or even we have a smaller term like constant C, then it makes sense to infer that the final solution should also be changed, right? So if based on our observation that these two are quite related to each other, right? So it makes sense to infer that the final solution is very much related to the function here. Okay. So this is the most salient relations that we need to use in the master theorem or master method. Okay. All right. So let's look at this so-called master method. It's basically a very simple, well, very easy to use cookbook for solving recurrences in this form. Okay. So it is the input, the condition of the input for master theorem. So we must have the recurrence in this form. All right. So if the recurrence is not in this form, then we cannot use master theorem, right? It's the limit of this method. Okay, so it must be, it must look like this. We must have some A, some B, and some function here. Okay. So these A and B's, they are constants, and f of n is some asymptotically positive function. Okay. That is the only requirements we want to place on f of n. Okay. So given this form, the master method says that we can directly obtain the solutions for T of n. We will have 3 conditions. In the first condition, it says, if we find the f of n here is bounded by this function, the function is n raised to the power of logarithm with base b of a minus some very little number constants, okay, for some constant epsilon. Then if this condition satisfies, then we can directly get the solution that T of n is bounded by n to the power of logarithm base b of n. Okay, right? So in a plain language, it says if f of n grows slower than this polynomial function, right? So it's basically a polynomial function, and the number here in the in this position is the order of the polynomial term is logarithm base b of a minus some constant. Okay. All right, that's the first condition, and the second condition is a little bit tight. Okay, it says if the function f of n has a tight bound, okay, it grows almost as fast as this polynomial function, then we can have our solution in this form. Okay, it's a polynomial term times a logarithm term. Okay, that's very interesting, right? So because this polynomial term times logarithm term reminds us of the running time for merge sort or maximum subarray, which is n times logarithm of n, right? So we'll later see if master method can provide us the correct solution to these common recurrences. All right, let's quickly look at the condition 3. Okay, the third condition is a little bit longer. Okay, so it says, as we can guess, if this polynomial function so the question in the chat is that does the epsilon is included in the logarithm function? Yeah, that's a good question. So the epsilon is outside the logarithm function. Okay, epsilon is outside logarithm. So the logarithm is just applied to a. Yeah. So it's basically the logarithm with base b of a. Yeah. Okay. So yeah, it's easy to guess the third condition. So the third condition says that if the polynomial function is the lower bound, okay, it grows slower than f of n. Okay, then it comes with an additional condition, which is that a times f of n over b is smaller or equal to c times f of n. Okay, for some constants c that is smaller than 1. Okay, then if these two conditions are satisfied, then we can claim that the solution for T of n is f of n itself. Okay, so as we can summarize by having a glance of these three conditions, it's just there are several key quantities that we are comparing with. First of all, it is this polynomial function n raised to the power of logarithm base b of a. Okay, so this is a polynomial function, and we're also concerning about the function f of n. Okay, so essentially we are comparing these two functions. We're comparing these two functions, and the first statement, if we look at it from an intuitive perspective, and that is to explain it using plain language, right? The first case, the first condition basically says that if the polynomial function is a larger one or it grows faster, then the solution is dominated by this term, by this polynomial function. And in case 3, otherwise, on the opposite side, if f of n is a dominant function, then the solution is also dominated by that f of n, right? I think that is intuitively, that is very easy to remember, right? We just need to choose whichever is the dominant term. And in the second condition, which basically says that the polynomial function and the f of n, they have the equal order, equal growth order, equal growth speed. Then we say that the solution is one of each, right? So these two big theta, they have equal meanings, have the same meaning. So we just use either f of n or the polynomial term times some logarithm term. Okay. So and that is all about everything about master method, right? So given this theory, or given this method, we are able to solve recurrences very quickly. Okay, as long as the recurrences, let's look at the condition again. As long as the recurrences looks like this form indicated by the dashed box. Okay, as long as we know A and B and f of n, then we can immediately tell the solution. Okay, so now let's look at some examples. All right, so before that, there's some technicalities that we need to pay attention to, because there's an epsilon here. So this epsilon a little bit tricky. Okay, it's not totally neglectable. Okay, it is there for a reason. So in the condition 1, it basically says that the f of n should not only be smaller than the polynomial function, but it must be polynomially smaller. Okay, it must be smaller than the than this function with the factor of n to the power of epsilon. So this epsilon can be very small, but it should be a positive value. Okay, so as long as we can find such an epsilon, no matter how small it is, then we can satisfy this condition. We can satisfy that f of n is polynomially smaller. Okay, so this is quite important because sometimes a function is in the lower order than the other one, but it is not necessarily polynomially lower. The most famous example is the logarithm function. So if we plot the logarithm function, that's yx, right? Basically in this shape, right? So this is 1 and this is 0. So if we plot the logarithm function here, and if we compare it with the linear function, y equals x, okay? So the polynomial function is y equals logarithm of x. Then we know that the linear function is always larger than the logarithm function, okay? But it is never polynomially larger, okay? Because the logarithm function is lower than any polynomial function. If we plot x, y equals x to the power of 0.001. So this is a function that grows really slow, right? But it still grows faster than the logarithm function. Okay. Yeah, so let's we will see a more concrete example to show in what cases we should pay attention to this polynomially smaller condition. And this condition also applies to condition 3, right? So in condition 3, the f of n should not only be greater than the polynomial function, but it should be a polynomially larger term, okay? We should at least find some epsilon, and this epsilon can be small, but it should be a positive number, okay? And another additional condition for case 3 is that these inequalities should satisfy, okay? But usually speaking, this quality is satisfied by most functions, by most polynomially bounded functions, okay? So if you look at the form of this condition, it basically says that if your input decreases, right? Because n over b is smaller than n, then the output should also be bounded by the original function with some constants as the constraint. And this quality is usually satisfied for most functions. Okay. All right, with this technicalities stated, we can look at some examples on the next page. Okay. All right, so if we find that some functions do not fall into these three cases, then we cannot apply the master method. Yeah. So basically, there's some gap between case 1 and case 2. So case 2 says that the two functions grow at the same speed. They have the same order. And the case 1 says that f of n is smaller, is polynomially smaller. So there's a gap between these two cases, which is that f of n is smaller, but is not polynomially smaller. And also there's a gap between case 2 and 3, which is f of n is larger, but not polynomially large. Okay. So these two special gaps are the cases that cannot be handled by master method. All right, let's look at the example now. So let's start with some function that we already know. At some recurrence we already know. Well, it looks like this, right? We all know the maximum salary problem. The solution looks like this. And now let's directly use the analysis, use the method, which means we know the constant a equals 2, and b also is 2, and the function here, the f of n here, is a linear function. Okay, so all we need to do is to compute the quantity n to the power of logarithm base b of a. Okay, so the logarithm base 2 of 2 is 1, right? So this polynomial function is a linear function. It grows at the same speed as the f of n here, okay? Which means the second condition applies, okay? So according to the theorem, we can directly have the solution, which is g of n equals big theta of n times logarithm of n. Okay? That's very straightforward. Okay? Now let's look at some other ones, other examples. Okay. Now let's consider these recurrences. So it's a quite big difference, right? So the appending function f of n here is a n times logarithm of n. Okay, so now let's compute, do the computation, right? So a and b are still 2, which means the logarithm, the polynomial function is n. Okay, and it's easy to say that to observe that the function f of n is asymptotically larger, right? Because it's n times logarithm of n, okay? And the logarithm of n is also monotonically increasing. So this function must be at higher order than the linear function. Okay, but we need to think about whether this is actually the case 3 that applies. Okay, we can think about this. The case 3 actually requires that f of n should be polynomially larger. We need to find some epsilon, right? We need to find some epsilon that's to describe the f of n, so that f of n is polynomially larger than the function, right? So can we find the epsilon, the positive epsilon, such that f of n is greater than this quantity, then this polynomial function. Right. Of course, we know that here it is 1, right? The quantity here it is 1. Okay. Actually, not. Okay, because this quantity, this inequality actually requires that if we substitute the form of f of n into the inequality, we will have n times logarithm of n should be greater than or equal to c times n to the power of 1 plus epsilon. Okay, if we eliminate n, it will indicate a logarithm function should be greater than or equal to a polynomial function, okay, with some epsilon. But we know that this is not doable, okay, because the logarithm function grows slower than any polynomial function. Even if this epsilon is a really small positive number. And then if we consider the function n to the power of epsilon, it has a higher order. It grows faster than logarithm of n. So that means eventually, as n increases, eventually we will have n to the power of epsilon that is greater than logarithm of n. Okay, so that is some mathematical property that we need to keep in mind for particularly for analyzing the recurrences that has logarithm functions involved. Okay, so the logarithm function grows slower than any form of polynomial functions. Okay, so unfortunately for this case, we cannot apply the master theorem or master method to directly get the solution. Okay, but it doesn't mean we cannot solve it. We still have the recursion tree method and the substitution method, right? We can draw the trees and to estimate the depths of the tree and estimate the per level summation, right? Use the same trick that we did using from the previous lecture. All right, so here's the first example that we find the masked method may not apply. All right, so a little bit more examples. Now we have 9 times t of n over 3. So a equals 9, and the logarithm of base 3 of a is 2. Okay, so this is an apparent case for the first condition, right? So the f of n is a linear function, right? So the f of n can be bounded by this quadratic term, okay, right? So when epsilon that is smaller than 1, then this quantity always hold, okay? So this quantity is always hold. So the n square function, this quadratic function is polynomially greater than the linear function. That is something for sure, right? So case 1 applies, then we can directly say that the solution is bounded by the higher order term, which is the quadratic function. Okay. Now a new example. Okay, so now a equals 1 and b is 3 over 2. If we consider this polynomial term, right, it's n to the power of 0, which is 1. Okay, and 1 is the same order as the f of n here, which means the case 2 applies. Then the solution is either one of them times logarithm of n, right? So the solution is the big theta of logarithm of n. Okay, all right, I think this is the last example we put here. We have a equals 3, and b equals 4. Okay, so now we can compute the logarithm of base b of a, which is logarithm base 4 of 3. So this is a approximated number, which is almost 0.793. So we cannot write all the decimals here, all the numbers here. Okay, so now let's look at the relationship between these f of n, right? So this is our f of n. We need to compare this n times logarithm n with this polynomial function, which is n to the power of 0.793 something. Okay, so actually the n times logarithm of n is indeed polynomially larger than this function, as long as we are looking at epsilons that are smaller than the difference between 1 minus 0.793. Okay, because when we consider n times logarithm of n, it's the product between n, right? N is also n to the power of 1, right? N to the power of 1 times logarithm of n. Okay, so since logarithm of n is smaller than any kind of epsilon, any kind of polynomial function, so we basically need to compare this term with this polynomial term, right? Okay, so this term is polynomially higher than this term as long as we are considering epsilon that's smaller than their difference. Okay, so the condition 3 still applies. Okay, and also we can show the regularity condition also hold. Okay, so the regularity condition says that we want a times f of n over b, which is 3 times this one, should be bounded by c times f of n, which is c times n logarithm of n. And we basically can solve this as long as c is 3 over 4, then it must be true. Okay, so the solution is that is the case 3 is to use the case 3 of master method, which means we need to use big theta of n times logarithm of n. Alrighty. Okay. So we have that many examples provided, and we also have some questions that we can work on in the second assignments. So it is indeed a really convenient function a way to solve recurrences resulted from divide and conquer algorithms. And many of you may be wondering why we can use such a method. Why we can compare f of n with some polynomial function, which is n to the power of logarithm base b of a. So what does this quantity mean? So now we can look at the way we prove the Master Theorem.
Okay. Oh, that's a quick question.
Yeah.
Can you go back to the last slide?
Mm-hmm.
And so how come this particular example, we had to prove the regularity condition, and like the other ones, the case just applied, and we didn't have to prove any,
I mean, yeah, this is the regularity condition, right?
Okay. So so there's a case 3 has a regularity condition that we have to prove for it to be case 3? Okay.
Yeah, that's correct. Case 3 is a little bit special. It's ask for this regularity condition to be satisfied.
Mm-hmm.
Yeah. So we need to find such a C that makes this inequality always hold. Okay. So if we eliminate the n's over there, basically says that let's see. if C, yeah, so if C is 3/4, then we basically would have this negative number that is always that's smaller than 0. Okay.
Okay, thank you.
Yeah. Give me a second. All right. Okay, so let's go on to the proof of Master Theorem. All right. There are 2 steps we will go. So first of all, the proof of the Master Theorem is quite similar to the way that we use for the recursion tree method. We basically will look at what the tree will look like for the general case of A times T of n over B, right? So this is general case for specific trees like T times 2 of n over 2 or 4 times T of n over 3 something, right? So we'll look at if a tree looks like this, if we have A branches in each split, how would be the tree like? Okay. So there are 2 steps we will take. The first step is to prove the lemma, okay, which reduce the problem to a new problem of evaluating an expression that contains a summation. Okay. And the second is to determine the bounds of this summation. Okay. So yeah. So the whole thing, the whole proof is not like a required content for this course. But I'm going through this quickly so that you will have some idea of why this is the case. So you will know more about why Master Theorem works in that particular way. Right. So the lemma 1 says that given the A, given the B that are constants, and A is something that's greater than 1, okay, then f of n is a non-negative function, okay, that is defined on some exact power of B. Okay, so that makes things easier, right? Because when we divide n by B, if we have n that is a exact power of B, then the whole division would be can be done without any remainder, right? So we'll define the T of n as this, which is the way we want, right? Which is the form of Master Theorem. Then lemma 1 says that the solution can be expressed by this equation, okay? Which the first item is the quantity that we are familiar with, which is the n to the power of logarithm base B of A, okay? And the second is a summation term, okay? It's if we just first look inside, it is a compound product between A to the power of J times f of n divided by B to the power of J. Okay, so and the range of the summation is from 0 and logarithm base B of n minus 1. Okay, so I hope this range reminds you of some properties about the recursion tree. Okay, so when we drew the recursion trees in the previous lectures, we call the top level, the root node, as depth 0, right? And this logarithm base b of n minus 1, it probably refers to the level that is 1 above the bottom level, right? Okay, so it's basically the form of ranges over all levels for the recursion tree. And for each level, we will have a summation in this form. Okay, so at least before everything we will show in the next slide, it looks like this form, right? The whole solution looks like this form. So now let's go through the steps to see if this is the case. Okay, so all we need to do is to draw the recursion tree. Okay, the f of n is something we put in the root node here, and each division would result in n over b, right? So if we substitute n over b into the equation, it will be something like n over b square, right, plus f of n over b, right? So that's why there's f of n over b to the level, to the depth 1 or level 1. Okay, so one thing that we didn't show here is that we cannot plot all the branches, right? Because a is a general number here. There's a numbers, so we just plotting 3 branches to showcase. Okay, all right. So, and the boundaries, the bottom levels is constant. Okay, that is also from the definition of the recurrences. Okay, so given this tree, right? We just need to do the same thing that we did before. We just look at each level. Okay, so the first level, level 1 or level 0 or depth 0, is f of n apparently, and the depth I, depth 1 or level 1. So because it has a branches, and each branch has the node with the value f of n over b. So we can use a times n over b as the summation for level 1. So one more level down, level 2, we will have a to the power a squared times f of n over b squared. Okay, and at some depth j, that's something we can infer. Then there are a to the power j nodes. Okay, and each node has a cost as f of n over b to the power of j. Right? And we multiply these two quantities together. It's this quantity. Right? This is already something we are looking for, right? Because we want to prove in the summation. Yeah, we want to prove that. So this is almost there. We're almost there. Yeah, we got a quantity here. So once we got this quantity here, we need to sum up the cost for all nodes. So we sum up each level first and sum up all the levels now, which is, so before that, we need to consider the leaf nodes, right? The leaf nodes, each node at the bottom level is a leaf node. And one leaf node, and first of all, let's consider the number of levels in the whole tree. So when the node hits the size of the node, the value of node hit 1, which means when j is logarithm base b of n, we are hitting the bottom level. Okay, so it also means the leaf nodes are at the depth logarithm base b of n. All right, and how many nodes are there? We need to use a to the power of j, right? So it's actually 8 to the power of logarithm base b of n, that many leaf nodes. And if we swap the a and n according to the principles of logarithm and exponential functions, it's n to the power of logarithm base b of a leaves. Okay, so this is the first time that we obtain this magical quantity, which is n to the power of logarithm base b of a. Okay, which actually refers to the number of leaf nodes in the recursion tree. Okay, all right. So if we sum up all the leaf nodes together, because each leaf node costs constant amount of time, then in total, the costs of solving all the leaf nodes is this big theta of n to the power of logarithm base b of a, right? And having leaf nodes solved, let's look at the internal nodes. Okay, so the internal nodes, now we have the range defined, right? It ranges from depth 0 to depth logarithm base b of n minus 1. We have a minus 1 because we need to stop one level above the leaf nodes, one level above the bottom level. And we just need to sum up all the levels, and each level is this quantity. So we just let the range, that the summation ranges from 0 to this one level above the bottom level. All right. So putting these two parts together, we can immediately get the form for the solution. Right. That's what we want to obtain from lemma 1, and it's lemma 1 is proved at this step. Okay, so we're pretty happy about that, because it's not an easy problem. We have abstract values like a and n, and we want to solve them with some mathematical expressions, and we did it. Okay, the T of n looks like big theta of this polynomial function plus this summation of some complex terms. Okay, so the next step is to deal with this complex term. Okay, we basically want to compare the summation parts. Okay, we want to compare these two parts. The blue parts is the cost for solving all the sub-problems of size 1, because it is the bottom level. All the bottom levels are the smallest cases. Okay, and we want to compare the cost with the second part, which is the cost of all the internal nodes, which means the internal nodes means the cost for the dividing and the combining steps. Okay. All right, so yeah, now we can think about the Master Theorem again. It essentially actually describes how the total costs are distributed among the nodes. And in the case one says that if f of n is a lower order function than the polynomial function, then which means all the costs are dominated by the costs in the leaf nodes at the bottom level. Okay, and in the case 2, the costs are evenly distributed among all levels or among all nodes in the recursion tree. Okay, and the case 3 is actually that the cost is demanded by the internal nodes, all the root node, because the root node has the biggest value within all the internal nodes. Right? All right. Now, the curious part is how do we determine what these parts, what the yellow parts, what the summation, what is its upper bound, okay, and lower bound for these parts. Okay? That is what we do for the Lemma Two. Okay, and Lemma Two basically says that if we denote this complex term as some function g of n, okay, it has these following bounds. Okay, if the f of n is a lower bound, is a polynomially lower bound, has a polynomially high upper bound as the polynomial function here, then we can say the g of n is dominated by the polynomial term. If they are in the same speed, f of n and the polynomial term are in the same speed, then g of n is logarithm times is the polynomial term times the logarithm term. And in case 3, if this regularity term satisfied for some constants, then the g of n is bounded by this f of n. So it's basically the same condition as the Master Theorem. Okay. So let's quickly go through how we prove Lemma Two. Okay. So it's still case by case. So case 1 says if f of n is a lower order function, is a smaller function, then it basically implies we can directly write from this condition to this equation. We just substitute n with the n over b to the power j. It's a simple replacement, okay? And we can substitute these parts into the g of n, okay? And everything we have becomes becomes this summation of aj times these more complex terms. Okay, so it may look more complex, but actually we can find a way. And remember, there's a big O there. Okay, big O means the upper bound. Okay, so we now eliminate the f, right? We eliminate the f, replace it with some upper bound. Okay, but things will be easier because now we see that we can further simplify. We can combine the a and b's because they have the same index j, right? We can put a and b together under the power of j, right? And also the logarithm, the b raised to the power of this term, right? And there's the n is also moved out, right? Because this whole thing has nothing to do with j, okay? So everything in here has something to do with j, okay? All right, and then if we do the further simplification, we would only have what? It's the b to the power of epsilon, okay? So it's actually a geometric series, right? It's actually a geometric series. And we can use the formula for the summation of geometric series to compute it, okay? Right? So it's actually something quite simple. It's bounded by this polynomial function, okay? Right, which we can further write into big O of n to the power logarithm base b of a. Okay, and in that case, our case 1 is proven. Okay, so the the trick is to do the substitution. Okay, to substitute the unknown function f with its upper bound, and because it's there's a j in it, and we can treat the whole thing as a geometric series. Okay, and let's look at case 2. The case 2 says f of n and the polynomial function grows in the same speed. Okay, we can do the same substitution into g of n, right? It's still the magic to replace f with this term with j, right? So it's again, we turn it into some geometric series. And the good news that it's a special geometric series that we have all once. Okay, and it's basically the form of polynomial term times some logarithm term. Okay, so case 2 is also proven, and case 3 we basically do the same thing, but with some additional regularity conditions. So the regularity condition says a times this f of n over b should be smaller than this one, which means we move the a to the right, it will be like this, and we substitute the n with n over b, right, to each side. We will have this term, and substitute again, we will have this term, and again with this term. We will substitute n over b into n by, like, in an iteratively. We will have a bunch of inequalities, and if we sum up all the inequalities, we will have the original term should be bounded by this summation, okay, which is also a term, a geometric series, okay, and we will find that it is bounded by the big O of f of n, okay. So altogether, we can have the 3 cases proved, and the Lemma 2 is proved, and we are almost done. If we combine Lemma 1 and Lemma 2, we can soon have the conclusions of Master Theorem obtained. Okay, and all the 3 cases, if we put them together, it's just the form for Master Theorem that we need. All right. So the previous 4 or 5 slides are about the proof for the Master Theorem. And I think it will be helpful if you go through them yourself to have some deeper understanding of why Master Theorem in this case. So so today I'm going to end the class a little bit earlier. So the assignments for the second assignment is already released. You can start working on it. And on the next Tuesday's lecture, we're going to talk about the last example of divide and conquer algorithm. So we might not be using the whole class talking about the algorithm, but after the algorithm is done, we are going to enter the next topic, which is sorting algorithms. All right, so that's pretty much the plan for today. Yeah, there's a date for midterm. I need to check my calendar. Should be March the 1st, I think. Yeah, it should be covering the divide and conquer algorithms and the sorting algorithms as well. Yeah, I can make it into the announcements. I think it's already in the syllabus. If not, I will make an announcement.
Yeah, there's no due dates. It's kind of just you kind of just gave like a general idea of when's gonna be idea, but there's like not a specific date.
Okay. Yeah. Then I can make announcements on
Oh.
Canvas. Yeah.
And March 1st is a Monday.
Then it should be the time in our class. In class, yeah, it should be Tuesday something.
Okay.
Yeah.
Thank you.
Yeah, no problem. Yeah, I'll double check and make an announcement for sure. Yeah. So yeah, that's for today's lecture. Thanks for coming. I'm going to end the record for now.